Okay, so because of time, we will start now. So first, thank you everyone for coming, and also everyone online. So I'm Francisco Forster. I will be chairing the session, and Marcio Catalan here will be co-chair. So Marcio will be keeping track of time, and he will also check the Slack channel. Okay. So just a brief intro. So this is the session for you to make sure that you're in the right session. A reminder of the code of conduct. You have seen this in all the talks. So you're free to wear a mask if you feel like. And yes, so also I want to note that. Sorry, wait, I haven't shared slides remotely. No, I am sharing slides. Yeah. This session is going to be followed by another session led by Brian Miller at 2 p.m. in Madera, which is another room that doesn't have online connection, I think. So unfortunately, for people connected online, they cannot attend the second session, but for those here, it's like the continuation of this. So this is identification of transient, and then this is the follow-up. And just for motivation, I wanted to share this slide. So and ask a question. So if I have something like this, a light curve like this, I have image stamps where there is a galaxy with something in the middle or in the outskirts. I have a lot of points where nothing happens, and then one of a few points that are detections. So the question is, should I trigger follow-up or not? What is the minimum information I know I need, and what is all the things that you can consider? So I made a quick list. So first, there is reliable DI source, perhaps more than one. That's related to Ignacio Reyes' talk, image stamps. There is a galaxy in the line of sight with redshift information, other properties. There's many other sessions on photometric redshifts. I didn't want to include that for that reason. There is no star in the template. The Milky Way extinction is not very large. And maybe there are multi-messenger, multi-wavelength cross-matches in space and time. So these are related to Tom, my talk, and Igor. And then there is lack of variability before the first detection. The light shape looks okay. And let's say you ignore the first detection. The non-detections are going up a little bit. This is also an indication that there's something real. So I just put in everything that we take into account when we determine whether something is real or not. And these are related to the talks by Rob, Alex, and Alex. So both Alex. Okay, so with this, I will leave Tom to talk about cross-matching in crowded fields. Tom, can you share your slides?
Yep. How is that?
We can see it.
Perfect.
So you have 7 minutes plus 3 of questions.
Okay. Thanks, everybody, for being here either in person or virtually. And I'm sorry I couldn't be there in person myself. Today, I wanted to talk to you about robust cross-matches in the crowded LSST sky, none of which I expect to be particularly controversial, because we all know that the Rubin Observatory's survey will be revolutionary in many aspects, but one of which is the data will challenge the models. So I'm hoping to convince you today that there's a bit of a trouble brewing in the identification of transient sources that will come out of the brokers and the alert stream. But I hope to convince you by the end of the talk as well that we know how to handle these problems and that there are steps that we can take to essentially model these extra effects that I'm going to talk to you about. Where essentially when, as was just illustrated quite nicely, an alert goes off because the source has become brighter, we want to combine that one wavelength detection with all of our data, either historic, so going through Rubin back through time, or perhaps going to other catalogs in other wavelengths. And essentially the question on the left here is just ultimately, is this source that we have detected, or are our two sources, left, red and black on the left hand there, one real source, or are they two physical sources, in which case we shouldn't combine, say, an infrared data point with our Rubin transient detection. And if you've used cross-matching before, and I know that quite a lot of the brokers have implemented nearest neighbor matching as their very simple, very quick, very efficient cross-matching algorithm, where you take your Rubin source and you just look at all the sources on the sky and you look for the thing with the nearest position, which makes sense when you sort of consider images. They overlap. We want to sort of constellation map. This is all very convenient. But there is a problem brewing with the Rubin Observatory's LSST, which is one of number counts. Where on the right-hand side here, I'm showing expected cumulative number of sources in a reasonably typical nearest neighbor circle that you might draw on the sky. And for every single image visit in the galactic plane, this is, of course, there will be one interloping object within these circles that we draw. And at 10-year depth, so if we want to go to faint progenitors, for example, there will be up to, say, 6 or 7 or 8 of these in every single circle. And now it's much harder to figure out which source is the correct one. In the more well-behaved extragalactic sky, this is maybe only 1 or 2 interloping sources, but that still gives you a large false negative rate in your cross-matching. So we can turn to Bayesian or probabilistic cross-matching, which combines 3 useful pieces of information. One is we can consider more than one source match simultaneously, where you see it in my rainbow circle picture on the left here. I've added some other sort of orange dots to consider a multi-source assignment consideration. Another that doesn't matter for transient sources, we can consider the brightness of our sources within the same framework, but by definition, if a transient object has just become 5 magnitudes brighter because it's gone supernova or something, we don't want to use that piece of information. But the third most important thing is that we can consider the precision of these rainbow circles, their size on the sky in my little schematic on the left there. And this tells us that we can reduce the length scale over which we are considering our potential cross matches from 2 arc seconds to maybe 0.2 arc seconds, gaining a factor 10 or 100 in area, much reducing that false negative rate of 4. But what these rainbow circles tell us is essentially the probability of the object's true position given where we measured it to be. And if you take nothing away from this talk, it is that the generalized, what I would like you to now think of them as astrometric uncertainty functions, can be any form, but that there is an assumption made in, I think, literally every paper ever to date, that these positional errors of sources are Gaussian. And this does not need to be the case in crowded fields. Because if we extend the assumption that the astrometric uncertainty function isn't just a Gaussian, we can include other effects in the uncertainties of the positions of our sources when we consider going from our Rubin object back to our legacy data or our ancillary surveys. So on the left here, I'm plotting a distribution of 2 different sets of Gaia wise matches. Or I'd like you to think of Gaia as the true position of these sources because Gaia has such good precision. So essentially, this is a distribution of deviation from true of these wise sources, where wise is a very useful proxy for LSST because they suffer roughly the same level of crowding at their completeness limits. And I'm plotting 2 different distributions, red and black, in this plot, and they're just at 2 different places on the sky. But all of the objects in these distributions have the same quoted uncertainty, and that should give us the black dashed line in the deviations from true if it was the only source of the astrometric uncertainty function. And I hope you can tell that the black dashed line here does not go through either of my sets of data. So what do we need to add to get the solid black and red lines to go through those data? So the astrometric uncertainty function's main Gaussian component comes from the noise in the images that we get. So again, I've got a picture of a little bit of Y's here, and you can see in the background, depending on how good the monitor in the room is, that there's sort of salt and pepper in the background. There's noise in our images, so when we say we get a centroid of our sources, there's a bit of scatter in the centroid of these objects due to that noise. But as you can also see, these objects are two-dimensional on the image. And what happens is, because these bright objects are physically two-dimensional on the image, they block out the light from fainter objects behind them, where if I plot the density of objects all sort of shifted onto each other, we can see there's this dearth of sources about inside 10 arc seconds here. Those objects don't go anywhere. They are blended. They are hidden within those brighter sources, and they are now unresolved contaminants, and they cause an additional deviation in the measured position. So if we do not take this into account, we get a high false negative rate in our matches where we say two objects aren't matched when they should be. And just to give you a sort of sense of the scale of this problem, here I'm showing you some examples in the galactic plane. So this is perhaps for microlensing, where we want to follow up lots of objects in the bulge to find planets and all sorts of things around these sources. Where on the top here I'm showing brighter sources, and the lower row here is fainter objects. So we've got perhaps single visit and a full 10-year depth. And then we've got two different parts of the sky, so two different levels of crowding. And I hope you can see that in various places, my blue and my red lines, again, are not compatible, and therefore we have this high false negative rate. But in the extragalactic transients, as most transients will be, they'll be outside of the galactic plane, we still have this problem. It's just much reduced because we're not suffering this level too much due to the much reduced crowding. But even if I want to take my supernova, which has popped up in a single visit image, and go back to my 10-year depth, or however many years depth we have to find the progenitor of some sort of cataclysmic variable, etc., we will see that when we try to find the progenitor in the more crowded image at 26th magnitude, there's still a detectable difference due to these blended contaminants in the astrometric uncertainty function. And that will cause perhaps a 5% change systematic bias in the cumulative distribution function in the probabilities. So if you're taking a probability cut in your the separation, say 3 sigma, 5 sigma detections, then you could be biased by up to 5% of your sources. And just very quickly to say that this also matters for the second data set that you're looking at, not just Rubin. So other data sets that suffer crowding in significant amounts, such as WISE and Herschel, you have to take this effect into account for both of your data sets. And I will skip this slide because I'm running out of time, and I will just leave my conclusions up and say thank you for listening.
Thank you. Any questions? We have time for one question. Can you hear?
Yes.
So in most of this, you showed circular error regions. So if you move to elliptical or non-parametric error regions, how do you deal with that?
So in our paradigm, that is not easy to do because we rely on circularity to make computational gains. So that if that was a significant factor of your science, we would have to consider how to handle that. We use circular uncertainties for computational reasons at the moment. But if it was a reduced data set, and therefore you could take more time over running the maths on a reduced number of sources, you can do it. But the software that we've developed doesn't do that at the moment. But that's a computational problem, not a mathematical problem. So it's all completely compatible.
Just to comment, most galaxies aren't circular. And
yes,
so
but if you get the positions, are the covariances of where you've centroided them not reasonably circular?
If you look at the stellar distribution, they're not circular, right? And that's what matters.
Okay. So if galaxy position covariances are significantly non-circular, then that's something that I need to know and we need to discuss. Yeah.
Okay. So we need to move on. Thank you, Tom. Thank you for. Well, I will share my slide. I will listen now. Okay, so Marcio, you tell me the time. I'll share, sorry. Okay. Okay, so now I will talk about host galaxy identification method that is called DELIGHT. So these are the authors of the paper. And this project is quite interesting because it was born out of the La Serena School of Data Science. So we had this data set. We wanted to do this project. We put it in the school, and actually we came with something interesting that evolved a lot, but became actually a useful product. So the problem that we have is that we want to have a real-time host galaxy identification that is reliable, so that we can, so reliable that we will actually point an 8-meter class telescope to this source. So there are two ways to do this, either from a catalog of galaxies, use, for example, the smallest normalized distance, or directly from the images. And we go for this second approach. So for this, we have the problem that if we are using input images and we want this to be fast, we want to use images that are large enough to include large galaxies and that have large enough resolution to see the very small galaxies that are more distant. So we want images that can do this, both of these things. So for this, we go for multi-resolution images. And what we do is we look for inspiration in nature. So the visual system, you don't have the same resolution in the center part of your visual system as in the outer parts. And you see these two images. We change the resolution in the outer part, and you can still detect the two galaxies. Okay, and so in this way, you can use lightweight images that could be used for a neural network to identify the host. So we implemented this, and the way we do this, we start with a 2 by 2 minute image from pan-stars, centering the position of the transient. We run Sextractor to remove stars and background. And then we transform these images into 2 by 2 minute multi-resolution images. So these multi-resolution images, actually 5 levels with different fields of view, different pixel sizes, but the same number of pixels. So actually use 2% of the bits that you need for the large image. So this could, in principle, be a string. And then we try a convolutional neural network to predict the host position. So this is kind of a regression example. And you predict the displacement vector. So we did this. We didn't know if this would work, and actually it worked. It worked really nicely. And so we compare with other methods. So the comparison we have is human labeled true position. So true is human labeled. The closest match, so the closest the nearest neighbor. Sextractor predicted position using the normalized ellipsoid distance. Directional light radius, that is used a lot in cosmology community. Another image-based method, which is called gradient ascent by Alex Gagliano, who's presented in the same session, and this work. So this is the result. In here, you see the comparison of the identification in the position error in arc seconds as a function of the separation between the transient and the center of the host. So you have large hosts that usually are larger separations, and smaller hosts are small separations. So what we see is that our method leads to fewer catastrophic errors. So the errors, although they are not as tight as in the DLR method, for example, we don't see this, the identity line populated by distant galaxies that are mistaken for the nearby galaxies. Okay, and if you look at the errors, the distribution, the characteristic error is less than 1 arc second. And the most important thing is the most robust method. So if you want to do the redshift association, this will work better. So then we tested this. So first thing, we compare as a fraction of the spectroscopic redshifts that we found, and as a fraction of the photometric redshifts that we found, our method was the most complete. So, and this is the order of how much of those redshifts we get. And this is the distribution of the redshift errors. So one thing is getting a redshift, and the other is what is the error in the redshift. And what we see is that, again, we are the more complete and the most pure. So we define a contamination a difference in the redshift of greater than 0.05. And we have less than 1%, actually 0.9% of contamination. So it's the more complete and purest of all the methods in the test sample that we use, which is based on CTF candidates and augmented with data from the Asiago catalog and the Hecate catalog of nearby galaxies. Okay, so then can we do this for Rubin? Normally, today we're using timestamps to get the images, which take about 5 seconds per source, which is very slow. Then we look at timestamps, and we're using the FitScat CGI routine, and this takes 3 seconds. So we said, okay, let's build our own heap server. And using our own heap server populated with Pan-STARRS image in the R band, we moved this to 200 milliseconds. And then we said, okay, but heaps is multi-resolution. So can we take advantage of the multi-resolution of heaps? We moved to 38 milliseconds. And then can we do this in parallel in 10 jobs? And we finally moved to 4 milliseconds, which is more or less the alert rate of LSST. So it's possible to do this in Rubin. And this was done by a computer science student, Diego León. So this is summary. Delight is a host identification algorithm using multi-resolution Pan-STARRS images. Something I didn't mention is that we use this to associate candidates in TNS reported by LSST every day. And here are the other conclusions. And you can install this with Astro Delight. So thank you.
Thank you for really nice walk and talk. I have a question about porting this pipeline to LSST. So first, will you have, as a LSS broker, have opportunity to have all image data, reference images to build these stamps? Yes, and second, probably this estimation is, lower limit estimation of time to reduce stamps because resolution of LSST will be better, so images will be larger, right? So how you're planning to port it for
so
LSST?
one way to prepare for LSST is use simulated images first. And in principle, if you have, let's say, the first year templates, you could populate your heap server perhaps with a lower resolution because you don't need very high resolution for this to work. And you could even compute the displacement vector in advance, or you can do it in real time because this is actually quite fast to run. But yeah, there are many questions that we need to solve.
How do we get data? Yes, and what about data rights? Yes, and really the whole of the data. How do we work?
Yeah, so the question is, how can we download the data? And you mean proprietary data rights and these kind of things. So this is something that we need to talk to data management team in LSST.
Sorry, quick. What's the trade-off and how would you explore the trade-off between size of stamp and resolution hierarchy?
Yeah, so we tried this when we were training. We tried different hierarchies, and this was that gave us the highest accuracy and F1 score and all the metrics. For the bigger galaxies, you cannot keep going up because this will be too expensive. So perhaps you need a parallel galaxy identification method for the largest, nearest galaxies.
Given that this is postage stamp based, have all of the broker teams, and I see at least 3 of them represented in this room, advocated just getting these multi-resolution postage stamps directly in the alerts from project itself?
This is not postage stamp based. This is based on Pan-STARRS.
Sure,
yeah.
but in
It could
principle
be.
for Rubin, it
Yeah.
could be postage.
Yeah, it could be. Yeah. So thank you for the question.
Any further questions? Franz? I'm afraid this.
Yeah, well, so kind of linking the first talk and your talk, right? As you go deeper, you're going to have potential to have interlopers, and at least this method, you're actually removing the stars and some of the other things. So what's the scope for putting them back in and actually doing this sort of a little more properly?
It's open I mean, there's a lot of things that can be improved. But in the highest resolution image, you should be able to see the nearest stars well. So in that sense, I don't worry too much about that. And a distant star will not be the host galaxy. So.
Okay, let's thank Francisco again.
Okay, so the next talk is by Ignacio Reyes, and it's related to this one. Ignacio, can you share your slides?
Okay, give me a second. So, can you hear me?
Yes, we can hear you.
Okay, great. So I will activate this laser point. Okay, hi everyone, my name is Ignacio Reyes, and I will talk about a paper that we just released last week in the Astrophysical Journal Letters related to use of multi-scale stamps, these kind of multi-resolution stamps, for classification of alerts in the stream context. So a little bit of motivation. Well, we are part of the LSST broker, and one of the models that we have running doing classification is the stamp classifier. And basically, we try to take the stamps, in this case from CTF or another survey, and to classify them into 5 or 6 classes, like some of the ones that I'm showing here. Variable stars, active galactic nuclei, bows, asteroids, supernovae, etc. And these have worked pretty well for LSST. So up to now, we have reported more than 18,000 supernovae candidates into the transient name server. LSST is the 3rd highest supernovae reported worldwide. And since 2021 to now, 30% of the confirmed supernovae in TNS worldwide have been found thanks to LSST. So this is not just to brag about it. This is because we have noticed that automatic stamp classification is important. It's really important. It's really useful for detecting transients and detecting them as early as possible. So one thing that we have noticed are these kind of stamps also, where you have like one source in the center, but also you have this trail, and we think of them as like a pearl necklace where you have these bright points as well as here. And what are those things? Apparently they are satellites, or maybe they can be something like this. Well, we don't know, but these things also have been reported in a paper by Karpov and Piloton, and apparently they're mostly satellites in some, or actually debris. Not the very bright satellites, but debris and stuff around the Earth. And what will happen with Rubin, at least considering the current specifications, is that the LSST image stamps, the image cutouts, in the alerts will be very, very small in terms of angular size. They are planned to be at least 30 by 30 pixels, but given that the pixels are really small in terms of angular size, the overall image is small. So in the case of LSST, we will expect just to catch the center point here, but the stamp will miss all the trail. So at least just looking at the stamp would not be possible to catch these kinds of objects. And what can we do? Because the size of these stamps is mainly limited because of internet bandwidth for the distribution of the stamps is one of the main restrictions here. So we evaluated what would happen using multi-scale, basically having a high resolution in the center and then these blurrier images with high field of view, with a larger field of view. So we did some experiments with CTF, and we evaluated something like this, like having a high resolution in the center and then larger scales in terms of angular size with like thicker pixels that way. And we did some experiments using CTF because that's with the data that we have available. And we did some classification with this. Basically, we compared the full stamps. In the case of CTF, they are 63 by 63 pixels. Some small stamps in terms of angular size, some blurrier large scale stamps, and this multi-scale approach that we are proposing. And the thing that we find out is that basically the F1 score, the F1 score macro, comparing the full stamps with the multi-scale stamps is pretty much the same. And you have a worst F1 score using the cropped stamps and the low resolution ones. And here are some confusion matrices, and I want to highlight some of these numbers. For example, comparing the cropped stamps that would be similar to the Rubin in the sense that they have a small angular size. The satellite recall is much smaller in the small size ones than in the comparing with the multi-scale. Another difference is that the amount of satellites that get confused with supernovae improves a lot when you use these multi-scale stamps and when you have access to a large field of view, like 3 or 4 times. And also the supernovae recall improves, so you miss less supernovae, which is very important for astrophysical reasons. So what are we proposing for Rubin? These are the current specifications. The image cutouts have to be at least 30 by 30 pixels in size, which gives you something in the ballpark of 6 by 6 arc seconds. And we think it would be a very good idea to use something like this, like having like the full quality images in the center by 16 by 16 pixels, for example, and then having these different scales that increases in field of view with like thicker pixels. Yeah. And that would improve, for example, the overall field of view going from 6 by 6 to 25 times 25. This is a proposal. So basically the conclusions here are that no other evaluated strategy besides the multi-scale was better in terms of F1 score. The current LSST specifications have stamps with a very small field of view, and this could have a really negative impact in terms of early detection of transients and having real-time detection in terms of minutes after the first occurrence of the transient. And we advocate that LSST should consider and should implement this strategy, but this will require all the feedback from the science collaborations, because this might impact how different science cases do their job in terms of real-time science. It's important to mention that there are other ways to access the full image, the full science image. If you're not in a hurry, you could wait a couple of days and then go to the service if you have the data rights.
Okay, Ignacio, I think we have to move to questions. So we have 2 minutes. Any questions for Ignacio?
Very nice talk. I just want to make everyone aware that you know, with respect to the glints especially, the Rubin team is thinking about how we can identify those upstream during the processing as it happens, and probably not eliminate, but probably flag those downstream, so that, you know, obviously doesn't obviate the need for brokers to classify those, but it's something that you know, clearly is a problem and a growing one, and so we need to make sure that we do as much as possible upstream, so that, you know, not just broker users, but also folks querying in the science platform and so on can get those points out of their data.
Thank you.
Yeah, my name is Nima Sadagat. I help with deep learning based transient detection at LSST. So I'm all in for a higher resolution stamp. I've been proposing it before, but I think if you want to dedicate bandwidth to 4 different resolutions, we could very well also, I mean, if you have 4 different images of different resolutions, you are spending 4 times the bandwidth. So
I'm sorry, just to confirm, it's the same number of pixels, the same number of bits.
yeah, I think I got that point, but let's say we have 30 by 30 stamps originally. Now we want to add other resolutions, but with the same number of pixels. Okay, okay, the proposal was that, because I thought if you want to have 4 different resolutions of the same size, you could as well grow the original image with the same resolution in each dimension 2 times. So because my experiments have shown that like a full resolution bigger image is much better than, I mean, degrading the resolution. But yeah, this all goes back to the bandwidth problem.
Yeah, so the thing that we tried here, I have it here. So the thing that we tried was to, instead of having the full image, when you go to the multi-scale, you do a smaller version of that one. And basically you don't have the same quality, but you preserve the number, like the weight in terms of like kilobytes or whatever, or number of pixels.
Okay, thank you, Ignacio. We need to move on. Full screen. To bring full screen. Anyone knows how to put this in full screen? F5? No. You see that? How do you put in full screen? Because I don't have. Right. Okay, thank you very much.
Thank you. I saw actually a mute button. Okay.
Remove this.
Okay, thank you, Francisco. My name is Igor Andreoni from University of Maryland and NASA Goddard. And I am here trying to answer a question that I found very interesting that Francisco sent my way in his invite email. What are the minimum ingredients to make good real-time classification based on your experience? That's an important factor. So this is experience and individual dependent. I'm not coming here trying to tell you that this is an absolute truth. And to be sure we're on the same page, the answer is also strongly dependent on your favorite science case. And definitely please throw more information at me. I'm gladly gonna take it, but I'm also aware that it's expensive sometimes and can slow you down to have too much information. So I'm definitely gonna try to go down to the very minimum ingredients to achieve our goals. Allow me to dig in my favorite science case, or one of my favorite science cases, which is try to find optical infrared counterparts to gravitational wave signals. We know that the counterparts can be bright from the radio all the way to the gamma rays. So once again, I'll focus here on the optical part. And this is why probably my intervention is also relevant for the session when we want to discuss fast transient. So fast in this sense, in this context, is from hour to days time scale. So generally it's more challenging to find kilonovae, this optical counterpart to gravitational waves, as compared to most types of bright supernovae. And on top of kilonovae, you may have also a gamma ray burst afterglow associated with a binary neutron star merger. Or in general, it's just fun to find afterglows in survey data, even without knowing that a gamma ray burst occurred. So that's something that we started doing more and more routinely right now. So I see also Francisco put me more like in the brackets of those who like cross matches, and I do like cross matches. In particular, cross matches that allow me to select region of interest if I have a trigger for sure, and definitely that allow me to tell whether a transient is real and is likely extragalactic. But on top of that, I think it all boils down when it comes to my favorite way to find fast transient is check the light curve. So do your query for the alerts and then try to look at the fade rate. That, along with other contextual information, can lead you to pretty interesting discoveries. This is why we developed the ZTF REST framework, ZTF real-time searching and triggering, in collaboration with Michael Coughlin and a team primarily based at Caltech. We want to do near real-time identification of possible extragalactic fast transients. And while we're doing that, we found dozens of supernova shock breakout, shock cooling, actually, several afterglows, in some cases connected to gamma ray bursts that then we found out being present in gamma ray observatory data, but in other cases, didn't have any gamma ray counterpart. And please look out for new papers that will be published in the next couple of months on this topic. Kilonovae, not quite, even if they are the main source, the main transient we are trying to find. We have not found any. We placed significant constraints in on the rate, but we did have some surprise, which is nice to do science on new type of sources that we managed to catch this way. So as you probably noticed in that very busy schema that I showed earlier, the kind of threshold that we set for our searches is 0.3 magnitudes per day of fade rate. It's not chosen by chance. It's based on study of distributions based on kilonova model grids. However, as you can see in this plot, here we just overplotted a bunch of transients that we identified, and you see how this parameter space is pretty well populated. You have on the y-axis the variation in R band, and on the x-axis time in days. So even for afterglows, depending on which phase you catch them, they really can appear evolving in different ways. And as I mentioned before, something unexpected can happen. So what we keep finding, fortunately, every now and again, every few months typically, are transients that we just cannot tell. We don't have enough information to tell what their nature is. But if we're good enough at using the information in hand, such as a combination of light curve evolution, color, contextual information, multi-wavelength cross matches, then we can send out a notification to the community. And if we're lucky enough, like in this case, we might find something that has never quite been observed before, or at least not been identified before in the optical. In this case, what we found was a relativistic tidal disruption event at high redshift, about redshift 1.2, and turned out to be the furthest tidal disruption event ever found, and indeed the first found by an optical survey. So it will be fun to see how many of those Rubin will be able to find, and if this type of a peculiar light curve that starts off as a fast transient and then becomes a blue and slowly evolving luminous transient will be folded in all the efforts for photometric classification. So for when it comes to kilonova discovery for Rubin Observatory, the problem is that we expect hundreds of kilonova to be present to have photons converted into signal of what some thought in Rubin images, but how many we will be able to identify. If you apply ZTF REST type of algorithms, we estimate from several to maybe 30, 40 kilonovae similar to GW17 or 17. This is when considering the WISE-FAST deep survey, definitely a lot of effort will be put in the follow-up of gravitational wave sources, in which definitely our chances will increase massively of finding a counterpart when we know when and where an event happens. So in conclusion, what in my opinion, in my experience, the key ingredients is that we need to be confident that a transient is real, have enough information to discern from galactic sources and other spurious and very spurious effect. If I had to pick one of the other features, I would pick the fade rate, but definitely other contextual information would be very, very welcome. Thank you again for your attention today.
Thanks for Igor.
Thank you. I have the same question again. How do you run it in the epoch of LSST? Do you run it with one of the brokers, or I mean, within infrastructure, one of the brokers, or do you run it on your cluster somewhere and consume data? So what are the model of running these type of algorithms for the future? Thank you.
Yeah, so at present, what we're doing, we are querying what sort of is an internal ZTF broker called Kowalski, but we can do the same job probably with Alersi, another type of broker. And at the moment, we're doing quite most of the analysis with a separate code running on a machine ST11 at Caltech. Although we are more and more trying to get some of the key information being processed even before, let's say, within the platforms that we use to inspect transients, and hopefully maybe in the future can also be integrated within the alerts if people find them useful, or perhaps the broker themselves are even a better place for that.
So one more question. Any time for more? No? So
Sorry if I blinked to stay 3, but is your quantification of the fade rate one of the statistics in the alert packet right now?
At the moment is not. It also depends how you define it. Because depending on the time span that you consider, you might have very different answers, and also you might be interested in a very fast rise in transient and so on. So once again, I think you really need to have the power to tweak it to your favorite science case to be able to make the most of this type of metric. It can't be universal. Unless you give me an array, then I'm fine with it.
But I mean, maybe there is an array. Is there an array of 3 different, I mean, Eric has slots for us to calculate numbers and make suggestions, not 100 slots, but I mean, I really appreciate the spirit of things. I think it's very much aligned to what gives the best. And if you can make this, I'm making up the number 3, but you understand what I'm saying, then I think that can be a very specific suggestion that might happen.
Thank you.
also a multi-band. It will be difficult to.
Oh no, all of this is computed for the same band. We don't mix up different bands for estimating the fade rate. There is too much degeneracy with color.
Okay, thank you. So now I think it's Rob. Can you share your slides, Rob? Thank you. We cannot hear you. Can you test your microphone?
How about now? Do you hear me?
Yes, a little low, so.
Okay, I can just try and talk loud. So Elastic, lessons learned, managing alerts in Elastic. Elastic is this thing we did in Desk to simulate alerts going out, brokers classifying alerts, and us ingesting them. There's a number of goals to Elastic, but the one that I'm going to be focusing on right now, you'll hear more in the next couple of talks, is just dealing with the fire hose alert stream that we're talking about. So the way Elastic worked is that we ran simulations of 4 million different objects. So it came up to 50 million different observations at NERSC. We also generated a training sample that we gave to all the brokers. Then over the course of 3 months, we sent out one alert for each one of these detections, each one of these 50 million detections, and we used the ZAD server because it was available, and thank you, Eric. And the brokers pulled from the ZAD server, they did their classifications, and then they pushed their classifications to us through a variety of different ways, which we stored them all in the DeskTom, which the URL is right there. If you're interested in getting an account on it, I'm the person to talk to. So that's what Elastic was doing. Now, so if we look at the rates at which things were happening, the top plot is the rate at which we were sending out alerts during Elastic. So this is just one day from the last week of Elastic. So you saw it at UTC 20 each day, we'd start sending them. We'd send them over the course of about 4 hours. We sent 500,000 alerts over the course of about 4 hours. The alert rate we were doing, so we have this 10 million alerts per night is sort of the back of the envelope idea we have for the number of alerts, which is consistent with what Francisco gave earlier is the alert rate. I was sort of relieved to see. And then we have this idea that in Desk we'll be interested in roughly 10% of them. And so this rate is comparable to the 10% rate, right? I guess 500,000 is 5%, but okay, within a factor of 2. So that's why we chose that rate. And then that's the rate at which we sent out the alerts. That was our simulation of LSST alert production. Then we had 5 different brokers who all ingested those alerts, did classifications on them and sent back to us. And you can see that the rate at which we got alerts back was different for different brokers. Fink, which was doing some just binary classifications, is it an early supernova or not, could basically classify alerts as fast as they got it. And in fact, sometimes the delay time of us ingesting their classifications was more than it took them to classify the alerts. And Terry's knew that they were under-provisioned for this. And so after the first few weeks, they fell behind. And that's why the rate at which alerts were coming back were pretty steady throughout the day because they were just working on backlog. And then Alercy was running at about a rate where they could basically complete a day's worth of alerts in a day. So if you look at the completeness, Alercy and Fink both had very high completeness, and Terry's completeness started high and varied and then got very high right at the end again. I'm not sure exactly what happened there. Maybe they just turned up, said, let's just do the end batch, something like that. So that's just all about the alert rates. Now we're planning Elastic 2, and we're going to stream at a higher rate. A rate that's about 3 times as high. So why this rate? Well, it's still not over the course of a day the full rate at which LSST is going to be sending out alerts. But the rate at which we are sending out alerts is approximately 200 per second right now, which is pretty close to the 250 per second that we anticipate from LSST. So that's the rate of the original alerts. So Elastic 2 is currently in early plumbing tests. I've been talking with several of the brokers about making sure we have everything connected together and been working on pulling stuff back. So what have I learned dealing with all of this? Well, one of the first things is writing Avro files actually turns out to be kind of slow because it's opening and closing and writing lots of little files. And so that's what we originally did. Is we took all of the detections, we wrote Avro files, and then we read and streamed them. So we went instead to just reconstructing the file and sending it and never writing, lots of small files to disk. Okay, good idea. The defined alert formats is a challenge that happens. So we're sending all the alert schema lists, The reason being the schema is stable throughout all of Elastic. So we don't need to repeatedly send the schema every single time we send an alert and every single time we receive an alert from a broker. That would be gratuitous bandwidth use. However, that does mean that we have to be using the same schema on both sides since it's not embedded. One of the, there's the sort of general alert infrastructure. If you say, oh, people are sending alerts, is usually either too general or too specific in that if you want to make a format that's going to work for everybody, it's going to be awfully general, and then you almost always need to customize it. And so then you have to know which survey you're dealing with, and you have to adapt to handle the alerts of that. Receiving alerts, so the ingestion rate versus maintaining structure. So one of the problems is that when Alex Maltz talks, he's going to tell you about various metrics and stuff. And to do that, we need to be able to join the tables of classifications to lots of other tables so that we can compare rates of things classified as various types to the true type, to how many times it was detected, so on and so forth. Well, so if the rate at which alerts come in from the brokers is sort of too fast for us to keep maintaining all of the structures, all the tables with indexes and foreign keys on them. So we have to deal with that. That's one of the things that we have to deal with, just the alert rate is so high. Another challenge that we had in Elastic is that brokers are sending alerts in 3 different formats. So there's the Kafka servers. One of the brokers is using Google Pub Sub, and then one of the brokers is actually posting to an API. So we have to make sure that we're able to handle all 3 of those in a consistent manner so that we can compare them with each other. And then I have a future worry, is that I mentioned early on that we think Desk is going to be interested in only 10% of the alerts, but I'm not sure what the mechanism for identifying those 10% is. If it's what the brokers classified it as, then we have to ingest everything. So I'm not sure what that answer is, but that's something I worry about. So I will stop there and see if anybody has any questions. I should note that I can't see the Slack, so I'll need the questions out loud.
Thanks a lot, Rob. That's very hard work. Thank you. Any questions for Rob?
Hey, Rob. In terms of saying what you want, I mean, I think any of the brokers in slightly different flavors you can define a filter or can define a stream. Is that something you want to try to test over the next couple of months?
It's something, yeah, not over the next month, because Elastic 2 is going to start in September. And so I don't want to try and add stuff to that, but that is the sort of thing I would want. Yes. And so, so if brokers themselves can define filters, that could solve that problem. Yes. So that, different topics for different things based on the filters we define, say.
Go on.
So partially actually in response to Michael's query, I actually am in the camp of we should have a copy of all of the alerts from all of the brokers or the classification reports. We don't need to have the full alerts. And then we run an ensemble classifier within Desk's own infrastructure where we can control it and test it a little bit more. Right. So I mean, I think
if that's
but what I will add here is if you saw Rob's slide where he had a desk TOM, there's nothing about the desk TOM that is desk specific. So you should think about this if you're in a different science collaboration as just general infrastructure to store alerts from different brokers and let you do your science downstream from them. And if you're interested in using that infrastructure, we can either give you the code, or if you want, we can also sort of work with your science collaborations and set up some kind of like intercollaboration agreement so you can use our deployment at NERSC.
And that the way at which the specific details of how it works is under heavy development right now at all times. That's part of what Elastic is for, is figuring out the right way to do all this.
Any more questions? So can you remind us the timescale for Elastic 2?
So Elastic 2 is going to start at the end of August 30th, something like that. I don't remember the exact day. It will run over the course of a month. I've been sending out test streams that are going to run at the same rate as Elastic 2. So this is the rate at which Elastic 2 will go. It'll start end of the month. It'll run for a month.
Okay, thank you, Rob.
Great. Let me stop sharing.
Okay, we can see your slides.
Perfect. Okay. Thank you everyone for joining. I'm sorry I couldn't be there personally, but I am very excited at all the conversations that we've been having. And I think it's a really nice session that brings together kind of the discussion of host galaxy information and how we find it, the types of machine learning methods that we're using to find events early, and what kind of science we can do when we find those events. This discussion very naturally leads into a paper that was just accepted a month ago, in which I and a few colleagues explored how we might combine host galaxy information and the earliest moments in a supernova's photometric evolution to better classify these events. Okay, so surely most of you in the audience are familiar with neural networks at this point. Recurrent neural networks have become commonplace for photometric classification of supernovae. And the value of recurrent classification lies in the predictions updating in real time as you get better data in. So maybe you have a tentative classification in the first few photometric observations, and then as your data gets more reliable and the supernova brightens, then you tighten up your constraints on the class you believe that phenomenon to belong to. There are a few limitations to the photometric models that have been built to date. One of them is, as Alex Maltz mentioned, peak brightness is a feature that is used to distinguish between supernovae. There are many others. Decline rate is another one. A lot of features that are calculated on the full phase of the light curve. And for this reason, a lot of events do not do well in real time on observed samples. When they do well in real time, it's on simulated samples from plastic and elastic. I'm involved in these efforts. I will not argue that they're not important. They very much are. But at the end of the day, we will always face a jump when bridging the gap from simulated data to observed data. And then on the right, you can see how this works for plastic, or excuse me, for rapid, which was applied to simulated samples from plastic. Okay, and then the next limitation, of course, is scaling up to the types of data volumes, as you heard about in Rob Knopp's talk, that are just going to become commonplace in a couple of years. There was a paper that came out recently that found that for a neural network model that was put as a filter in a broker, a significant computational bottleneck was just loading the model into memory. And this pushes us to start thinking about how simply we can make our models, because you are going to need to be regularly reloading the model and retraining as we get more data in following first light. Now, my focus has been on incorporating host galaxy information as priors to the types of events that we think we're going to see. There's precedent to doing this type of analysis. Here are the results from two different papers, one in 2013 and one much more recent, that basically found that by aggregating properties of a sample of nearby host galaxies, you can make basic cuts for what type of event you think that galaxy will host. And so unsurprisingly, by making a cut, for example, on star formation rate, you can distinguish reasonably well between core collapse and type 1a supernovae. And this has all been done offline in the past. So the question we wanted to ask is, how could we incorporate this information in real time? How can we do this on real data? And we jumped through a lot of hoops to actually get this to work. On the left, I'm showing a walkthrough of how this works. We use Gaussian process regression on partial phase light curves and concatenate on vectors of the photometric redshifts of the events from their host galaxy photometry and their host galaxy photometry directly. And then all of this information gets piped into a single layered neural network that is smaller than both rapid and SCONE, other archival methods that have been trained recurrently in this framework. And then we get out a classification prediction. And this framework we have validated on observed samples from the Zwicky transient facility after initial training on simulated data. So here is a set of results from this framework. On the left, you can see a ROC curve. The area under this curve for different classes parameterizes how well we're classifying these events. And this ROC curve is for events that we're looking at photometry of within the first 3 days. On the right, you can see the change in the area under the rock curves for different models starting 3 days after discovery and then improving after that. And you can see that all of these models do no better than random classification within the first 3 days. Random is in OROC terms 50%, and we do better than random in the first 3 days across all of our classes. So this is an exciting validation that this host galaxy information really is valuable. And as time goes on, because we're classifying recurrently, we're now taking advantage of the photometric evolution of the supernova itself to improve our predictions. You can see how at later phases, the area under the rock curve continues to improve. And this is quite exciting. And we're thinking about now extending this framework to other events for which you might have stronger host galaxy correlations. We looked at many different parameters. Lots are used to quantify how well you're doing in classification. And we found that every element of our training framework improves every mean classification metric, which is exciting. And just a small note, which points to the postage stamp discussion, morphology was a really valuable classification metric, a feature for classification in a 2013 paper. And I have a feeling that doing this in a convolutional setting using even small postage stamps would further improve our performance. So I'll end there by just saying that it seems like contextual information, at least in the 3-class problem, can improve our early classification when we have not much data from the supernova itself, but we should be developing our models to be adaptive to new data as more comes in. And something that I did not mention, but I just want to toss it out there, I'm now thinking a lot about how performant is performant enough? When is your classification good enough to trigger follow-up on an 8-meter class telescope? I think that question is very much underexplored in these types of papers, including in mine, and I would love to chat with people about that. Thanks.
Thank you, Alex. Any questions for Alex?
Hi, Alex. Is there a way to think about what the available information is and how well you can do in this space?
Yeah, beautiful question. So there are theoretical frameworks from information theory where you can make arguments and train a model to trigger. There are attention-based networks that do a kind of triggering on or off valve based on the information content of the data that you provided. I have not seen a model trained like that, but I think in theory, something like that could be done and would be very valuable.
Thank you.
Hi, Alex. Guillermo Cabrera from LSST. I'm thinking about how would a model like this work for the LSST, right? Because you will need some particular pieces of information from the host galaxy, but at the same time, you need to know that it's a supernova, right? That the alert comes from supernova. So how do you imagine this working in the LSST era?
Yeah, I have lots of thoughts about that. I think to your point about the host galaxy information, we only used broadband photometry and PhotoZs that you could either get from archival information and offline photometric redshift estimators or directly from the survey itself. In terms of performance on LSST data, we actually started training on simulated partial phase elastic light curves and found that it performed better, but we wanted to validate it on real data, so we switched over to a Zwicky transient facility. But I'm confident that we will have the relevant data products that we will need to do this type of classification. It will inevitably be downstream from other real bogus and more general classifiers.
Right, but you also need to first know that it is a supernova, right?
Yes. to be able to do this right. So again, it would happen downstream, but I think, right, okay, so I mentioned these methods needing to be highly scalable, which is why we opted for as simple of an architecture as possible here. I think something that is going to become common in the era of LSST is ensemble classifiers, each tasked with doing one small, simple task and aggregating the results for many of them. So this is one piece of the puzzle.
More questions? So, okay, you want to?
Okay, so this is a question on Slack for Alex Maltz. Have you looked at how the class probabilities behave across the nominal classes for objects in the other class?
Do you hear the?
Sorry, was it for Alex Maltz or Alex Galliano?
So Plastic had a major goal of having objects in the test set that were not in the training set. This was less of a component for Elastic. I can't comment on whether how big a component it will be of Elastic 2, but making those plots requires having a sample of true other. That being said, if we get lots of classifications or enough classifications of other from the brokers for like which classes are they classifying, then we can do some metrics of that and develop them along the way.
No. So I want to do an experiment. Can we vote on the question of this session? Are we ready? Who thinks we are not ready? Okay, so I want to emphasize this. So because sometimes in the papers, everything looks very happy and nice, and real life is not so easy. So we have 5 minutes left, which was to get ready. Exactly. Anyone wants to comment something or highlight something that was not mentioned in this session? Godam and France.
So I'm worried about two primary areas, actually. Like, folks showed really good host association, the connections to the brokers between the science collaborations, and Rubin, or at least ZADS, is working. The brokers are running classifiers. Science collaborations can get those reports back. But we've done this round trip only considering LSST simulated alerts. It'd be good to start working with real alerts, maybe from DECCAM data. It would also be good for brokers and classification teams to start thinking about how to combine multiple optical surveys, because LSST isn't the only thing out there. And you have more information, especially if something like ZTF is taking data at the same time as LSST. That's an open classification question. And then the bigger issue for me that I'm worried about that we try to address with this schema and taxonomy is, if everybody has their own little filter, how do you make sense of the reports from brokers? How do you make it in some kind of standardized format that anybody can use the output?
Any comments to the comment? Well, I think in this case, I mean, we need to work closely with the science collaborations and see what they need. But it's, yeah, of course, there's not one answer for this. France?
Yeah, I mean, the other thing to think about is that the first year isn't going to be very easy. Most of the things that you guys are talking about require data release 1. And so there's going to be a transition between those that, you need to think about.
So can I, that's exactly why I think it's so important to get the right input data and leave the responsibility to the input data and not to some other catalog that who knows when we will have it. And also, I think this Alex Gagliano talk is showing like where many of us are going, like multimodal, and use all the information we have. And perhaps the models that we use in 5 years have nothing to do with what we're doing today. So just make sure we have all the input data as soon as possible.
The problem is, for instance, in Alex's model, you're not going to have a catalog that's going deep enough to actually classify the galaxies the first year.
Can I comment on that?
Alex, yeah?
Yeah, I just wanted to say, so our training and our evaluation set for host galaxies, our training set was a normalizing flow trained on a characteristic sample of host galaxies that have been discovered in past surveys, and with photometry standardized across pan-stars. So the host galaxy misclassification fraction that is common for different techniques like DLR, that's included within our data model and in our training set. So I'm confident that we could do okay with that piece of things for the data input.
Okay.
I mean, the other cheeky thing one can do is just use the postage stamps themselves as the inputs rather than the galaxy properties derived from something, and that becomes a CRNN. But I completely agree with multi-resolution postage stamps, and Eric can shoot me later.
At a minimum, we need the templates. We need at least the template.
At the minimum, yes, yes. At least a service to get the template, multi-resolution. Yeah. Yeah, because now we are asking things to you, but then you will be asking us things to us brokers. So we understand that we don't want to put pressure. Any more questions, comments? If not, we can finish here. Thank you everyone for coming. And remember, there's a follow-up session about follow-up at 2 p.m. in the next room. Thank you.